So we see that if the rate of temperature change is proportional to what we call the temperature difference, we can write this equation, which is first order linear but non-homogeneous. Now, we can do a change of variable, and this is an important and powerful technique in mathematical modeling and in a differential equations course. I'm going to let tau equal T minus T room. Now my equation, it will become dt, d big T, d little t equals k times tau. Well, I don't really want to have two different variables, big T on this side and tau on this side, so let's just figure out what d tau dt would be. Well, let's see, d tau dt equals the derivative with respect to t of t minus t room. Now, it's presuming that the temperature of the room is constant, because if this temperature isn't constant, we no longer have a first order linear equation of any sort. If T room is constant, then the derivative of T room is 0, and the derivative of this expression is just d big T, d little t. In other words, tau changes at the same rate that T does. And that makes perfect sense if you think about it. This means that we can translate the equation, and the equation becomes d tau dt equals k times tau. This equation is first order linear, and it's homogeneous. So this equation can be interpreted as tau prime minus k tau equals 0 with solution tau equals a e to the kt. Now, determining the value of k, determining the value of a depends on the circumstances. It could be that you have an initial temperature that's lower than the temperature of the room, in which case tau would be negative, a would be negative, k might be positive, it might be negative, and we could worry about that in specific instances, but we see that we can take this statement of proportionality between the rate of temperature change and the temperature difference, translate it into the variable tau, and we'll notice that tau is the temperature difference. And write this equation in a simple form, which we've already solved in terms of compound interest, or we've solved in general, just using a different variable, using the variable p instead of the variable tau. Let's consider the equation y prime equals 0.01 t times y squared. Now, this equation is what we call separable, and I'm going to explain what that means. Y prime can be written, of course, dy dt, and it looks like we're blurring out. Let me see if I can recapture the focus here. Let's put this down here for the camera to focus on for a minute till we get something on the paper. Okay, dy dt then will equal 0.01 t y squared. This can be rearranged. Now, this is kind of a formal rearrangement, and we'll see why this works theoretically a little bit later maybe, but if we multiply both sides by dt and then divide both sides by y squared, we get dy over y squared equals 0.01 t dt, and we've separated the y's onto this side and the t's onto this side. We've separated out the y and the t so that we can integrate both sides. If we integrate dy over y squared, and there's no d there, that's dy over y squared. See if I can find something to kind of obliterate that error. So that's dy over y squared integral of dy over y squared equals the integral of 0.01t dt. Now that's an easy integral. Dy over y squared is negative 1 over y, the integral of dy over y squared. And the integral of 0.01t is, we'll do it in decimal form since I've got this in decimal form. That would be 0.005 t squared plus our integration constant. Now we still need to solve for y, but that's easy. Y would then equal negative 1 over 0.005 t squared plus c. So we've got a solution of this equation. Now if we have initial condition, and we can use a t-value hc. We also note that this isn't defined for all c. This is only defined as long as c is greater than or equal to negative 0.005 t squared, because, well, as long as c is not greater than or equal to, as long as c is not equal to negative 0.005 t squared, because if it is, our denominator is going to be 0. So that as long as everything's defined here, we have a solution. Now, another example, and I've written it kind of small over here. I made a mistake, which is why the dollar coin is there. But if we have y prime equals ky, then that can be written dy dt equals ky. Now I use this equation because we've already solved it in the case of compound interest, and we've referred to it as tau prime equals k tau in the case of temperature change in a room. Temperature change of an object in a room at constant temperature, to be more specific. So y prime equals ky becomes dy dt equals ky, and this is easily separated into dy over y equals k dt. That can be integrated. On the left we get a natural log, on the right we get kt plus a constant, and we can continue to manipulate the form of this equation. We don't want to get too far into the equation. We're going to see this equation a whole lot. The point is that this equation is a first order linear homogeneous equation, can be solved as such, but it can also be solved by separating the variables.